Okay, welcome back Year 12s. What I'm going to do in this video is go through the two modules, the key questions that were low scoring, in my opinion anyway. So what we're going to do is start with matrices. As you can see, we're going to start with matrices question 5. I'm going to go through question 5, 6, 7, and 8 of matrices, and then I've only got 2 to go through with networks because that one was answered so well. That module was answered so well. So number 5 in matrices, we're given a transition matrix and we're given information about population of birds at feeding at 2 different locations. We're told that in 2018, 55%, so I'm just going to call this S 2018, 55% of the birds fed at location B, which means, of course, that 45% must have fed at location A, given it has to be the rest of them. Now that we know that, we are asked in 2019 the percentage of birds expected to feed at location A. So we want this number here, but for S 2019. So all you had to do with this one is, now that you've established S 2018, is just do the transition matrix, multiply that by S 2018, and what you'll get is 5842. And so since we're asked for the percentage of birds expected at location A, we can see that that is 58%. So the answer for this one, question 5, was D. Number 6, as you can see, we've got some information about 2 matrices, and then we just have to state what matrix Q could be. So we're told that this is what we need. We want Q multiplied by W to give us W. So as soon as I see that, I start thinking about the identity matrix, because the identity matrix would allow that to be true. So what I would do then is work out, okay, how big is W? What sort of size are we looking at? And you'll see here that it's got, since we want Q times W, W is a 3 times 2. That's going to tell us how big Q needs to be, because you'll see that with the answers here, we've got lots of different sizes. So if we have a look here, I basically want to know, let's make that a bit bigger, how many rows and how many columns need to be in this. So for Q to multiply by W, I need these two to be the same, so that needs to be a 3. But the answer is going to be a 3 by 2, since W is a 3 by 2, which means that this number has to be a 3 as well, because we get the 3 by 2 from these outside 2 numbers when we multiply 2 matrices together. So Q has to be a 3 by 3, so then we eliminate these 3. And then I mentioned before the identity matrix, so we want to consider, well, which of these 2 will be the identity matrix, and it's clearly this one. But what you could also do is just consider, when I do a run and dive with this multiplied by the 3 numbers that are in W, that's just going to add them all together. Whereas when I multiply by this one, it's going to take my first one in W, and then it's going to do the same for the next one and the next one. So this is the only one that's going to actually give me, or it's not going to change the elements. It's going to keep the elements as they are. And so D is the answer. Okay, on to number 7. Fairly challenging one here. A, because you've got this gigantic transition diagram here. You don't actually need to use all of that transition diagram though for this question. So what we're told is it's all to do with cows, movement of cows. We've got week 23, the numbers for each of the 4 locations, and we've got for week 24 as well. So what's really important with these sorts of questions is that you can translate or comprehend what they're asking for here. So of the cows expected to be at Q in week 24. So Q in week 24 is this bit right here. There's 222 of them, and it says of those. So we're really just focusing on those 222 just there. So of them, The percentage of these cows, so of the cows expected to be at Q, the percentage of these cows at R in week 23. So how many of these, or how many, or what percentage I should say, let's take that out. What percentage of these ones, of these 222, came from R? It's essentially what it's asking. So in R, in week 23, so the week before, there's 240. So what we really need to know is how many of these 240 are going to go from R to Q. And this is where our diagram is going to help us out. So R to Q is just here. So the arrow towards Q, so 20% of them. So first of all, we can work out 20% of this number here, 240. And that'll give us 48. So what percentage of these 222 came from R? Was 48 of them out of 222 of them. And we times that by 100 to get a percentage. It'll come out as 21.6, which when rounded is closest to 22%. So D is the answer for this one as well. So really important that you look at when it says of the blah, 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 you find that focus first. And then you have a look at what they're asking you in terms of the transitions. It was talking about the cows that came from R to Q. We find that information from the diagram and we apply that percentage to see how many did go from R to Q, but then we express that as a percentage of that little focus group that they mentioned. So they are quite challenging, these sorts of percentage ones. I think there was one in your SAC as well, and you can see that it's starting to become a common one that is coming up in exams as well. Okay, so the last one in matrices, which is definitely the most challenging one, I'm going to run through a strategy to answer this one that's come up. So those of you who had a bit of an idea how to do this, you might have been looking at it and thinking, well, I need to do obviously my steady state matrix since it mentioned the long term. But the issue with this one is we didn't know what that initial state matrix was. That's not usually an issue as long as you know how many in total there are. So you can just put some numbers into your S0 and then you can find your steady state anyway. But the problem is we don't even know how many sheep there are. This was not the same as the question before. The question before was talking about cows. So we couldn't use those values there. We actually didn't have any values to work with. So one strategy that you can use here is you can convert instead to a percentage or a proportion. Once you use a proportion, then what you can do is you can solve for how many sheep. I'll show you what I mean. So we want to do T by S0, or we want to do a power on that. We want to do a high power. So say, I'll just take that out. Say we wanted to do T to the power of 100. So we can check that we get to the steady state matrix. Since we don't know what S0 is, what we can do instead is we know there's 4 different locations. We can just put 25% in each. Doesn't matter which way you do this. You could actually just put 1 in one of the element spots and that would still work. But just for argument's sake, say you just split the sheep evenly to start off with. So there's 25% in each. And then you apply your transition matrix to a really high power. And then you can have a look at what actual values you get. Now, what I'm going to do is label I'm not going to do it on my calculator just because of timing. It's 4x4 matrix will take forever. But in terms of steady state, if I apply this, this is our PQRS, you're going to get values come out. And they're giving you a proportion. So not giving you actual values, they're giving you really a percentage of how many are ending up in each of the locations. So when you do this, you're going to get for S, comes out as 0.31296. And the other one we need is Q. So I'll just write them in because they're the only values we're actually going to use. 26027. So roughly 31% end up at S and roughly 26% end up at Q. Now we want to know the number of sheep that will end up at Q. So we don't want just the percentage, we want the actual value. What we know is that 0.31296, so this is for S, location X, that multiplied by the total sheep gives us 635, because that's what we were told up there, that there were 635 of them. So that means that we can solve for total sheep and we get to the nearest whole number, 2,029 sheep that there must be. And so that, therefore, if we're looking for how many are going to be at Q, we can take the proportion that we got for Q, which was this value up here, multiply that by the total sheep, so 2,029 of them, we get approximately 528. So it's closest to this one, 527. So just in summary, I made up an S0 matrix using just proportions rather than actual numbers. So I split the number of sheep evenly between the four. It doesn't matter where these values are, like how you split it. I just split it evenly because I think that's probably the easiest thing to do. Then I applied this long-term matrix. I did check though, obviously, that it was steady, and it was. And then I used these proportions here and converted them to actual values to finish off. Okay, so that's matrices now. I'm going to skip ahead in networks. The first question I wanted to talk about was number 6. So networks was done really, really well. The first one was this one that I just wanted to touch on. It asked for how many of these graphs are planar. So how many can you redraw so that there's no overlap? So first of all, this one is already in planar form. So A cannot be the answer. There's very clearly one that is planar. Secondly, if I have a look at this one, I can very easily take that out. So that will take away this little intersection. And the only other intersections here and here, so I can just move that edge over there. So that one's also planar, so this one can't be the answer. I'll leave that one for a moment. This one over here, I've got an intersection just there, so I can move that. And I've got an intersection, the only other one is here. So I could move that one just around there. So that looks like around the intersection. So that's also planar. So that can't be the answer. And so finally we're asking, is it just this 3 or is this fourth one also planar? Now looking at this one, I first, I noticed that it's a complete graph in that every edge is connected to every other edge. And I also noticed it's got 5 vertices. So complete graphs where you've got V, number of vertices greater than or equal to 5 are non-planar. They always are. So this is not a planar graph. So you can, if you've got time, have a go at trying to get it to be planar or to try and draw it to be in a planar form, but you will find it very frustrating because it's not possible, and you can try many different ways and potentially waste a bit of time there. So the answer here was D. That is in your notes as well, by the way. So if you have a look at your planar graphs, your notes, you'll see there is one. It doesn't look exactly the same as that, but it is a bit of a star shape, obviously, as created like this. And it is the same graph. It's an isomorphic graph to this one that's just here. Last one that I want to touch on for networks is this one, and I've started it off just to save a bit of time. This one here is a crashing question, so thank goodness one has come up in the exam. However, we haven't approached it, or we haven't done super well on it, which is why I wanted to talk about it. So with this one here, what I've done is a forward-backward scan. I think it's essential in this particular question to do it because there are just so many possible paths through this network. So you wouldn't want to try and list every single path and its duration, because that's going to take you too long. So what I do, or there's a reason that I do this, and that's because the float times are really helpful for this particular question. So I've done my forward backward scan, and from that I can see that the critical path goes through KNQTU, and it's got a length of 23. So I've just put that on the side there. I've put another path in. I'll get to that second path in a minute, the reason that I've written that one in. But we'll just look at the question for a second. We've got the cost of reducing is 1,000 per day. Landscape gardener has a maximum of 3,000. So we can only take off 3 days, as in like off each activity. And we want to obviously get the minimum completion. So we're told here that he can reduce it by 3 days. So that's helpful to know that that's what's possible. Because from there, what we can do, or all we have to do is work out how you can do that. So what that means, if you can reduce this minimum completion time, that means that this path here, KNQTU, has to come down to a length of 20, because that is the critical path right now. So for him to reduce the minimum completion time, that means he must have brought it down to 20. So that's the first step in working out how to answer this question, because what you could do is you could go through some of these answers here and work out which ones might actually bring that down to 20. Now, the unfortunate thing is that a couple of them might do. I mean, if you have a look at A, if we take off 1 from K, so I'll just put a dot under K, 1 off K and 2 off Q, that will bring this down. If we do 2 off Q and 2 off K and 1 off Q, that will also bring that down to 20. So the reason there's one of these is going to be incorrect, or both of them, because we haven't gone through them all yet, is because there could be another path there that also needs to be reduced, or a different activity that also needs to be reduced. So what we can do is have a look at your forward backward scan, and the easiest way to find another path that's close to 23 is just look for something that's got a low float time. So what I can see in terms of low float times is I've got a float of 1 here and here, also with this M right here. So that's a clue for you that there must be a path that comes up through here that has got a completion time, or it's got a length that's 1 less than the minimum. The minimum completion time, so the critical path. So there's a path that goes through here that must be 22. So if I have a look down this way, so 6 and then another 8, so the 14, 21, 22, it goes through KNMOSU. So I've written that one there and I've written its length, because what that means is that this also has to come down to 20. If this path here is not reduced, then you could potentially create a different critical path. Now, if I have a look for any other float times, just in case there is another path there that's important, if I look at, say, R, for example, R's got a float of 3. So that means that there's a path that goes through R that's already 3 less than 23, so it's already 20. So I don't need to worry about that one, because if it's already 20, these ones are just going to come down and they're going to match that. So they're not going to, you're not going to create another critical path. There's not going to be a hidden critical path. And then every other float time is higher, so I don't need to worry about that either. So I'm really just concerned about these 2 paths right here. Then what I want to do is just find something that is going to reduce this down to 20, but it's also going to make sure this one comes down to 20 as well. So if you have a look at A, reduce k by 1, so take this off, that brings it down to 22, and q by 2, that works, it brings this down to 20. But if I only take 1 off k, this path here will come down to 21, not 20, as is required. So that there is not going to work. If we try the next one, so activity k by 2, so if we take off 2 from this one, and 2 obviously comes off that second one, and then activity q by 1 day, so take off 1, that will be a maximum of 3 reduction off this one, and it will be a 2 reduction off that one. So that will bring both of them down to 20. That works, and that's actually the answer. So the reason that C won't work, if you only take 2 off K, this brings 23 down to 21, so you don't achieve 20. If you take 1 off K and 2 off M, same issue. 1 off K does not bring this down to 20. And if we do 1 off K, 1 off M, and 1 off Q, you only get a reduction of 2 off of K and QTU. So again, that's not going to work. So really only a couple of options here that did reduce this path down to 20, but it had to be in this particular combination so that K in both of these two paths were also reduced. Okay, that was a bit of a mouthful, but that is how that particular question should be approached. Again, I would not recommend writing out every single possible path because you've got 1, 2, 3, 4, and then 5, 6, 7, 8 paths, maybe more there. And so that would just take far too long. So use your forward backward scan, which won't take you too long, and then use the float times to help you look at which paths are going to be important.